Welcome to Science and the Written Word. I'm Lou Massa. We have with us Dr. Rudolf Pariser. He has had a long and distinguished career at the DuPont Corporation. Now a consultant in research management, he also helped start an education program at the University of Delaware. I asked him today about an article he wrote in Chemtech, June 1998. The material was originally presented in a lecture at the Chemical Heritage Foundation in Philadelphia. The article is called Creativity at the Crossroads Between Science and Technology. Welcome, Rudy. Nice to have you here.
Good to be here.
In order to get us started in the discussion about this topic of creativity, I wonder if you could read this paragraph at the beginning of your article just to set the conversation.
Yes. What I wrote is about defining creativity, science, and technology. It's been said that creativity evades definition and even recognition. For my purpose, I'll accept the Random House dictionary definition for creativity: the ability to transcend traditional ideas, rules, patterns, relationships, or the like, and to create meaningful new ideas, forms, methods, interpretations, originality, progressiveness, or imagination. This definition conveys creativity is not merely novelty, but that it produces something of substance. I define science as being concerned with knowing why. That is, the understanding of nature. Science is discipline-oriented, whereas technology is application-oriented. Technology is concerned with knowing how to attain useful products and processes. The roads of science and technology have not always crossed. To quote the science writer Melvin Kranzberg, science historically stems from philosophical, theological, and speculative inquiries about nature and ancient societies. Technology, on the other hand, derives from arts and crafts carried on by humble artisans in the same societies. This dichotomy between science and technology persisted throughout the Middle Ages. It wasn't until the Industrial Revolution at the end of the 19th century that the roads of science and technology began to cross in a substantial way. At the beginning of this century, the creation of the industrial laboratory, which actually started to do scientific research, was a manifestation of such newly created crossroads between science and technology. And the DuPont company is a very excellent example of this.
Yes, thank you. That, I think, sets the framework for our discussion. Now, one additional thing, could you tell us something about your background and whether, for example, you've been in a position to observe creativity?
Well, I should have been. I was both a scientist and a manager and research director at DuPont for a span of about 38 years. In the course of that, I have certainly come across many very creative people in many different laboratories, ranging from highly applied research to what you might call basic exploratory type of research.
Yes. In your article, of course, you give us some examples. And one of them that interests me is this whole discussion of the discovery of zero differential overlap. Mm-hmm. Who are the people involved with that, for starters?
Well, it is known as, the overall theory has received the name of the PPP theory, of which I guess the first P belongs to me, and the next one to Bob Parr, good friend of mine, and the third to John Popel, who very recently got the Nobel Prize in Chemistry.
Yes, for computational chemistry.
Correct.
Right. Okay, can we go back to the beginning of this discovery? And I guess perhaps it would be useful to say that this is a discovery that has to do with how quantum mechanics can be applied to fairly large molecules. This is a very difficult problem as to how you would solve the Schrödinger equation for a molecule of some size, something bigger than benzene with more than 6 atoms, something that would go up into 10, 12, 20 atoms. Go back to the beginning for us. What were you involved in at DuPont that set you on this road to the discovery of what came to be called PPP?
Well, I was just a fresh graduate from the University of Minnesota. I'd gotten my PhD in photochemistry, not much connection with theoretical chemistry in a way. I came to the Jackson Laboratory at DuPont, which was a very interesting laboratory across the river from Wilmington in the Chambers Works, an old lab, very crowded, but in retrospect, an extremely creative laboratory. And at the time, there was a great effort going on there to develop new dyes for the new fibers that DuPont had introduced, like nylon, Dacron, Orlon, etc. It was the organic chemicals department, incidentally, that was at that laboratory. I was only one of 2 or 3 physical chemists there, and they didn't really know exactly what to do with me, and they told me, why don't you characterize these dyes, which I started to do by measuring the spectra on the DU spectrophotometer. It took me a whole day or so to get one spectrum, which today can be done in seconds, you know.
Yes.
So I decided I wasn't very profitable. And I thought maybe what I should do is try to provide guidance to these organic chemists as to how structures relate to color and other properties. I remembered a quotation by Dirac which went something like, and hereby, referring to quantum mechanics, hereby most of the laws of physics and all of chemistry is completely understood, and all that needs to be done is application. I felt that was a snap.
Dirac didn't say how hard this would be.
Right. Yes. So, not knowing anything about quantum chemistry, or just have had a course or 2 at Minnesota, I did remember Bob Parr being there and doing his PhD in that area. And so I decided I would go see him and see if we couldn't do something about it.
So you 2 were known to each other from your school days?
Yes. In fact, I had taken a course from Bob in thermodynamics, so he was a few years ahead of me in graduate school, but we did know each other well.
So you went to look up Parr?
Mm-hmm.
And what sort of person was he, and what is the reception that you found?
Well, I visited him at Carnegie Tech, where he had just become a assistant professor. I told him about my ambition, and what goes to his credit, of course, in retrospect, is that he told me, yes, Rudy, let's go ahead and do this. He didn't say it was impossible, which any sensible person would have said.
Exactly.
Right.
And what then were the steps that occurred? I mean, let's say in terms of the 2 or 3 breakthroughs that are associated with this discovery, what happened? What was the sequence of events?
Well, there was a theory available at the time called the Huckel theory, which treated large molecules, but it wasn't much good to do spectra. And in fact, the Huckel theory ignored what we call the repulsion between electrons, kind of averaged it all out. And we felt that we had to introduce that specifically, as was being done in the more sophisticated so-called non-empirical theories at the time. Of course, to do that, it requires an immense amount of computation. Took a whole PhD thesis just to do benzene or ethylene and how we're going to do huge dye molecules.
Right.
So nevertheless, we started thinking about it, and one day I got a letter from Bob Parr with a suggestion. He says, let's neglect the overlap between electrons. Now, to those who are not in chemistry, overlap between electrons is what creates bonding in molecules, and in neglecting that's almost giving up chemistry. But it was a daring approximation. But
you know, in terms of this question of creativity and so on, it seems to me that we're hitting at creativity, because it would be anathema from a certain point of view to suggest neglecting the way orbitals overlap and connect together. Is that roughly true?
That's precisely true.
So how did this suggestion strike you on receiving it?
Well, what I was looking at was the practical significance of doing that, because by neglecting this so-called overlap, the computation was, the work, the labor involved in computing was very much reduced. In fact, at the time we didn't have electronic computers, and I could do benzene on a desk calculator in just in an hour or two.
By adopting this zero differential overlap approximation.
Exactly. And get results which are practically the same as had been achieved previously with these lengthy non-empirical calculations on benzene. So that really excited me a lot.
So the tractability of the whole thing, the fact that it would make calculations possible, was a great draw.
Exactly.
Yeah.
Now you could even see the end in sight. You could calculate a dye-molecule, perhaps with a good deal of more work, but you could do it. But of course, what was the discouraging part of it was that the original calculations, as well as this one, did not agree with experiment, especially not with the spectrum, which is what...
Now what sort of molecules, after you've adopted this dramatic suggestion of neglecting the overlap of orbitals, what sort of system would you have tried at first?
Well, at first, of course, we just did it on benzene, say, and as I said earlier, the results were not very good.
So if you compare the theoretical prediction against the experimentally known result for benzene, you did not get the comparison that one would like.
Exactly.
So that seems discouraging.
That seemed discouraging. However, and we didn't go much further at this point because we had to solve this disagreement problem first.
Now there is a subtle point. Comparison against experiment is one thing, but then you could also have compared against the more or less exact theoretical results that were known, right?
Yes.
And they did compare, apparently.
They did compare precisely.
Yes.
Almost precisely.
Yes.
Yes.
So that's the really encouraging part of this approximation.
That's correct. Yeah.
So here you are. You've got this wonderful ability to do the calculations, but you're not getting the experimental answers. What happens?
Well, what happened was that since this theory of zero differential overlap or approximation that Bob had invented was so tractable, since I had been trained in kinetics and I was used to fitting empirical constants to rate equations, and I decided, why don't I work backwards and see what should these electronic repulsion integrals be in order to get the right result. And so I plugged things in from that direction, and I fully expected to get a lot of very weird numbers for these electronic repulsion integrals. The only ones that remained, incidentally, were the so-called Coulomb integrals, where the electrons are separated and sit on different atoms, or in one case where they are both on the same atom. Well, the interesting part was that
So you adjusted these empirically, just
correct.
Trying to see
To
how you could fit to the experiment.
Exactly.
And the upshot of that?
The upshot of it was that, to my great surprise, these integrals checked the experimental values pretty much closely, except for one integral. And that is the one that describes the electronic repulsion when two electrons sit on the same atom, 2 pi electrons in the same atom. And that one was way off.
What sort of a difference are we talking about?
Well, the theoretical value was about 17 electron volts, and the experimental value was about 11. Now, I saw 11, that really hit me because that sounded like the ionization potential of carbon. And in looking at it a little bit, it's...
And the ionization potential would mean the energy required to pull an electron off the carbon atom.
Correct. And one can very easily demonstrate that within the approximation of this theory, this 1 electron, 2 electron repulsion integral in the same atom should in fact equal the ionization potential minus the electron affinity.
And the electron affinity is the energy associated with attaching an electron
Correct.
to the carbon atom,
Correct.
or to an atom in general.
That's right. So,
So you got this wonderful idea that there are these experimental numbers, the ionization potential and the electron affinity, that you could take the difference of these two and assign that to this integral.
That's right.
So the theoretically calculated value of the integral was this number up around 17.
Mm-hmm.
But the experiment, I minus A, the ionization potential minus the electron affinity, is suggesting a number more like 11.
That's correct.
So you try this approximation, I presume.
Mm-hmm.
And were you able to justify it in ways other than the fact that it would fit the experiment? Were you able to justify it theoretically or quasi-theoretically?
Oh, yes. We, as well as others, spent a good deal of work on that. And of course, it has to do with the fact that we're dealing here with a pi-electron approximation that doesn't include all the electrons in the molecule. And what this approximation in a way does is it corrects for that neglect. The other electrons, of course, know where the pi electrons are, but in this general approximation, they're assumed to be rigid. The one electron integral is the one where the other electrons feel the presence of pi electrons the most, because there are two of them sitting on one atom,
Yes.
highly charged. And so the correlation between their motion and those of the pi electrons is probably, or no, is what accounts for a good part of this difference between the theoretical value
Yes.
and the experimental value.
So now we have these two great ideas that enter the theory, the zero differential overlap, and now this way of approximating the repulsion integral
Right.
that you referred to as ionization potential minus the electron affinity. So you adopt these great ideas, I gather, and you start computing?
Yes.
And what happens? What's the result there?
Well, the result was, I had to go to a larger computer to tackle things like naphthalene, anthracene, and so on. I went through the polyacene series. I used the very
Now,
first.
could you describe what that series would be? What does it look like? I mean, benzene is a little flat molecule.
Benzene is a flat
Ring.
hexagon, and naphthalene are two hexagons fused.
Right.
Anthracene are three, tetracene four.
Right.
and
So you went through this
I went
series
through
of
the
ever-increasing
size.
size,
Right.
which would have been extraordinarily difficult without these approximations.
Essentially impossible at
Right.
that time.
Right.
Impossible.
Yes. And you got results that you were able to compare to the measured spectra for these molecules?
Yes, we were, and they agreed extremely well. And what's more, we even calculated certain electronic states that are not readily observed experimentally, so-called triplet states.
And subsequently, these were found to be fairly accurate predictions.
Yes. Very accurate, in fact.
Yes.
In fact, strikingly so, almost scaringly so.
Yes. Now, you mentioned computers. Can you say a word about the role of computers? This would have been what, in 52 or so?
Yes.
Or 51, 52?
Right,
So-
about 52 or 3.
So this is at the very beginning of off-the-shelf computers of any sort.
That's true.
And so what was the role that computers played? Did they basically allow you to carry out the calculations?
Without them, we could not have done it, even with this type of approximation. I mean, without...
So in some sense, were you all among the first to do quantum chemical calculations on a large computer?
Well, IBM, where I did my work on Madison Avenue...
Not far from here, actually.
Not far from here.
Yeah.
Told me that I happened to be the first chemist to have used their computer, which was the 701. It was the
Yes.
first all-transistorized computer. We had tried vacuum tube computers previously, and we never got through the calculation because the tubes had burned out.
So it's a combination of these great ideas and the sort of oncoming of computers that allowed all of this to happen. It would appear.
Very much
Yeah.
so.
What about the working conditions at DuPont? Is there something about the way DuPont was run that allowed this creativity that we're discussing to come forward? And is that important?
It is important, and it is very important. In fact, the management that I had at DuPont was extremely supportive of this work. Bob Parr, he became our consultant, and so on. So having a supportive management and supportive facilities and a non-threatening atmosphere is extremely important, I feel, in fostering creativity.
Yeah, I would have to agree with that. Well, so that's a wonderful success story. You mention other examples in your paper, for example, the discovery of crown ethers.
Mm-hmm.
Could we go into that a bit as another example of creativity? You know, who was involved there, for example?
Well, to get right to the end point, the discoverer of the crown ethers was Charlie Peterson, who was honored with the Nobel Prize in Chemistry in '87. I was fortunate enough in the sense that I was, quote, the boss of Charlie, although we're going back in time here to Jackson Laboratory again, where Charlie was working as an organic chemist.
This would be the 60s, I gather.
It'd be the 50s, in fact.
50s, okay.
50s. The Jackson lab, or the department was the organic chemicals department, got split at the time into an elastomers department, which is a polymer department, and organic chemicals. And both Charlie and I transferred into the elastomers department. I won't go into the reasons why, but we did. And at this time, I was laboratory director of the elastomers department, the new elastomers department. Charlie was a research fellow, which is the highest level of research rank in DuPont. In fact, he was the only research fellow in the whole laboratory. So theoretically, he could work whatever he wanted to do, but Charlie was a very much industrial chemist. He wanted to have clear-cut objectives that would be useful to the company and so on. His background had been in stabilizing petroleum,
Mm-hmm.
and his major contribution there was to chelate copper ions, which tend to destabilize gasoline. And
How would one describe chelating? Is it a matter of a molecule having a geometry that allows the ion to fit?
exactly,
And
it's
attach?
like a jaw, a jaw that would, if this is the copper ion, you know, the jaw would grab it.
Yes.
It would be a
Perfect fit.
perfect fit. And so Charlie had developed such chelating agents for copper, which stabilized gasoline, petroleum products. When he moved into the elastomers department, that's a polymer department, he felt a bit strange and was looking for things to do.
And was he able to draw on this experience with chelating agents?
Yes, he was, because in the elastomers department we were working on ethylene propylene copolymers. These are rubbers, and the catalyst used was a vanadium catalyst. And the vanadium was, some of it was left behind in the polymer, tend to destabilize it. So Charlie thought, aha, maybe I can do something here. Maybe I could devise a chelating agent for vanadium that would deactivate the vanadium and stabilize this synthetic rubber, ethylene propylene.
So when he tried this, did he get what he was looking for, or something else?
Well, he was trying to synthesize this chelating agent, and in observing the mixture from his reaction, he noticed there was some pretty white crystals, a very small amount, but they were in there, and he didn't know what they were. He knew that that was not the chelating agent that he was synthesizing, yet his curiosity was much aroused. And he came to see me about that, actually, and he said, you know, Rudy, I'm very curious what those things are. However, I know they're not what I was after. And I also know that if I go after that, I'll probably waste several months and I'll be off on my objective. And that bothered Charlie a great deal.
But presumably you encouraged him to go forward, because he did.
I did, and he did.
Right. And what happened was he ended up discovering these beautiful crown-like molecules that
Right.
pick up the ions perfectly,
Right.
well
But
suited by their geometry.
what he discovered was that they were indeed circular type molecules that completely engulfed an ion. As it turns out, these so-called crowns, as he dubbed them, engulfed sodium, potassium, lithium ions, and he could synthesize these crowns, these circles of different sizes, and he discovered that the little ions fit the little crowns, and the bigger ions fit the bigger crowns, and they were...
It's like the beginning of molecular recognition.
Correct.
And that led to the Nobel Prize.
That led
Yeah.
to the Nobel
Yeah.
Prize.
Now, I know there are other examples of creativity beyond those we've discussed in your article, but just because time is going by, I wonder if we could try to draw out any general lessons
Yeah.
about creativity. From these examples, can one say something about what goes into creativity and results that are associated with that?
Yes, I can name several things. We already mentioned the fact that we need to have a supportive, non-threatening environment. Another thing that I would urge people to do if they want to become creative is to learn a new field, because I feel very strongly in all of these examples that I described, it resulted really from the marriage of different disciplines, like in the case of Charlie, you know, copper, chemistry, to vanadium chemistry, and from petroleum to rubber and so on, the marriage of different fields. And I think creativity has to do with that. So that is another aspect that is very important.
What about this crossover notion that's in your title, the science and technology coming together? Does that seem
Yes.
something that inspires?
I think in all of these examples that I describe in the article, the origination was really technological. The objectives, the goals were technological. The result in all of them was a strong contribution to science as well as to technology. And the people working on them crossed back and forth between science and technology, asking why and asking how all
Yes.
along. And I think that's very stimulating to creativity.
Yes. We only have a minute left, but one thing about this discovery of the zero differential overlap that intrigues me is that it's wrong in some sense, because in some very exact picture, there is overlap.
Mm-hmm.
And in the half minute or so that we have left, does that impress you that there is a that creativity drove the two of you to adopt these assumptions, which, although not exact, had this very pragmatic, get the job done quality to them? Is that sort of a driving motivation and a productive one?
Of course it is.
Yeah,
Yeah.
yeah. It impresses me that way
yeah,
too.
yeah.
The reason I bring it up is I think there is a type of scientist that insists on exactness to the point that practicalities are thrown away. You know.
Right.
So I found something very creative about the fact that you pursued those approximations that would give you the answers required. We're all totally out of time, so I will simply thank you, Rudy, for coming.